Good afternoon, everyone. First of all, thank you for the opportunity to come in today. We appreciate it. We were in, I think, about 2 years ago. Gave sort of an introductory talk to structural thermal brakes, more focused on concrete structures. But we had developed kind of a follow-on presentation of that. It gets much deeper into the building science and then also focuses a bit more on the steel structure side. So we'd asked if we could come back in and present that, and we're grateful for that opportunity. For those who may not have met me before or don't remember me, my name is Brent Chancellor. My background is, I got bachelor's and master's degrees in civil engineering from the University of Oklahoma. Then had a brain cramp, decided to go back to school. So I ended up moving to Pennsylvania, went to Lehigh University and got a PhD in structural engineering. After that, I moved to the New York City area, even though I told myself I'd never live there, somehow ended up there anyway. Worked for several years for Leslie Robertson Associates, designing tall buildings and special structures all over the world. And then out of the blue, Shook approached me and said, hey, we're looking to expand in North America. We're looking for someone just like you. Would you come join us? And after talking to them and getting to know a bit about the company, I felt like it was the right thing to do. That's sort of how I ended up traveling around and making these types of presentations. And just a little bit about the company and who we are before we get into the presentation. So Shook is a German company. The main German headquarters are located in a tiny town called Baden-Baden, which is in southwestern Germany, almost on the border with France. You know where Strasbourg, France is? We're basically on the German side of that border. But then our North American headquarters are just located just up the road in Princeton, New Jersey. We started out as a construction company back in 1962, but then evolved into a manufacturing company as our founder kept inventing new products to try to improve construction processes. And then today we're sort of known for being specialists in structural thermal brakes, which is what we want to talk about. But besides structural thermal brakes, the other stuff that we do, we make some double-headed punching shear reinforcement for very thin flat plate slabs, especially shear down reinforcement where we have to transfer loads across expansion joints. We're just starting to roll out a thermal bridge-free facade connector for ventilated range screen facades, and then we do a little bit of noise dampening solutions for stairways as well. So that's sort of the other stuff that we do, but the bulk of what we do, what we're known for, what everyone calls us up for is the structural thermal brakes. Today's presentation is AIA-certified. There's a sign-in sheet in the back. If you do want those credits, please just make sure I have your information before you leave today so that we can get you those credits. Now, today's presentation, what we want to do is start out by looking at why thermal bridging and thermal brakes are more important than ever in steel structures, and how the building codes are changing and what that's going to mean for us into the future. And because of those changes in the building code, we want to look a little bit deeper into the building science of how to thermally model these thermal bridges and what difference the thermal brake can make there. We need to talk a bit about condensation control, because if we're going to install a thermal brake, that's often what it's used for, in addition to not wasting energy. And then at the end of the presentation, what we'd like to do is go through a few of the solutions that are available on the market and kind of look at some of the pluses and minuses and where their strengths are and maybe their sweet spots are for those different solutions. So just to start out, kind of a recap of maybe what we talked about 2 years ago. So what is a thermal bridge? We build a building, and in almost every case, we have to pass some sort of structural element through it, the building envelope. Whether that's a canopy beam at an entrance, maybe it's some rooftop dunnage post, something like that. Somewhere on our building envelope, we're going to have structural elements coming across that insulation layer. And where those structural elements come through the insulation layer, because of the high thermal conductivity of that structural material, we're going to end up transferring a lot more heat at that location. So that increased heat flow is called a thermal bridge. And then if we look and kind of compare the thermal conductivities of different materials, and we're going to compare them all back to mineral wool, the thermal conductivity of mineral wool, because that's basically a nice standard insulation material. So thermal conductivity for mineral wool is 0.03. We look at plywood or a wood structure, it's about 0.14. So it's multiple times what your insulation is, but it's still not that terrible relative to some of these other materials. We get to concrete, it's 1.9, so many more times the mineral wool, although it looks fairly small on this bar chart. But then we get over to structural steel on the far right, and it's way off the charts, and its thermal conductivity is up around 47, and it's about 1,500 times greater than your typical insulation material in terms of its heat transfer through that material, and about 24 times worse than concrete, which is already bad. And so this is why, as architects, engineers, we need to start paying more attention to these types of connections in terms of as our energy codes, particularly, are getting tighter and trying to tighten up things around the energy use. Now, before we go forward, one thing I do want to point out is that if we go from structural steel to stainless steel, it's quite a large drop, even though stainless steel is still pretty bad. There's a significant improvement once you make that switch in material. And I want you to remember that because that's going to come up again at the end of the presentation when we start to talk about solutions. Okay. So what are the big issues that are typically associated with thermal bridging? There's the obvious one of energy loss. We're just wasting energy through that location where we have that structural element coming through the building envelope. Another thing is the risk of condensation or mold growth. That's particularly for steel connections, that's often a big issue, even more so than the energy loss. There can also be thermal comfort issues. And then as the energy codes are changing, if we're going to stay sort of in compliance with those energy codes, we need to be paying attention to this issue. But where do these types of problems occur in our buildings? So there's the obvious one here of a balcony. So anywhere where we have a balcony attached to our building, we're showing a steel balcony in this case, but it could be a concrete balcony or concrete slab. But anywhere where that steel beam is going to come through that building envelope and attach, any sort of canopy, sunshade, or eyebrow connection on our building, all the connections for those elements are going to be thermal bridges if they're not treated. Any sort of beam penetration through the building envelope. And in this example, the beams that pick up the load of the video board on the Viking Stadium. Rooftop dunnage or rooftop equipment, those posts that come down through our roof insulation layer. Kind of a different theme, variation on that theme. So screen walls, basically the same as rooftop dunnage posts, they just have much higher loads due to the wind load on the wall. And then masonry support angles. And masonry support angles are often a big one because there's the toe of the angle usually crosses the continuous insulation. Because it's steel, has high thermal conductivity, there's a lot of linear footage of it all the way around the building. In terms of energy performance of the building, can have quite a significant impact on the overall performance of the building. Okay, so since 1980, our residential buildings or single-family homes, their energy use has declined by something like 25% or more. And commercial buildings, it's about 50%. And most of those changes in energy use over time have largely been driven by changes in the energy code. So the energy code will get tighter. We'll respond to that. We'll design a tighter building in terms of energy use, and then that just steps down over time. But what's interesting is during that same time period, our washing machines and our refrigerators have declined in their energy use by as much as 70% or more. So the question becomes, why can't we get the same level of performance in our buildings? And if we pay attention to the right types of details, thermal bridges being one of those, then we can start to get that level of performance. And newer building standards, things like Passive House, are looking at that, trying to drive that number down to a very, very low energy use, or even down to net zero on our buildings. But sometimes when we bring up this issue, we get asked the question, say, well, you're talking about energy performance, you're talking about condensation. I've never really had problems with these types of connections on my buildings before. Why is it a problem now? And that may be true. But as the energy code gets tighter, and we're trying to respond to that, we're trying to design a more energy efficient building. One of the best ways to improve the energy performance of your building is to improve the air barrier and prevent that air loss through the building envelope. But what happens is, as we improve that air barrier and we tighten up the building, what's going to happen on the inside of the building is the relative humidity levels are going to rise. Often that's a good thing because in the middle of winter, we usually end up with humidity levels that are actually outside that healthy humidity level range. And that shows up as things like static electricity, or maybe nosebleeds or something like that. Those are associated with relative humidity levels that are too low. But as we tighten up the air barrier, push that relative humidity level a little bit higher, connections where previously we didn't have these types of issues, we may start to have problems with those connections. And so I really have to bring the whole building performance forward together, not just the energy side of it. Okay. But where are the building codes at with respect to this issue and where are they headed? So right now, all of the more recent versions of ASHRAE 90.1 and IECC all have a definition for continuous insulation that says that the only thing that can cross that continuous insulation layer is a fastener. Now, things like steel beams, concrete slabs, those are structural elements, they're not fasteners. And so the energy code would really like us to look at this situation and deal with it in some way. Now within the energy code, we've got several different paths to compliance. We've got the prescriptive path, we've got the building envelope performance method or trade-off method, and we've got the whole building energy modeling method. With the prescriptive path, it's almost forced into using something like a thermal break to meet some of those prescriptive requirements in the energy code. But many of the architects I've talked to don't use that method all that often. buildings we're designing today, we have to go to one of those other two methods to get them into compliance with the energy code. And with the other two methods, the building envelope performance method and the whole building energy modeling method, the energy code basically says that you can sort of ignore the problem at its source, either add a little more insulation or something like that somewhere else on the building envelope, or maybe improve your mechanical system in some way, and then say on balance, your building is performing equal to or better than a benchmark building. Now, it's great that the energy code gives us that much flexibility because we need that at times to design some of the buildings we're making today. But at the same time, it doesn't solve the problem at its source. That problem still exists. We're still wasting lots of energy at those thermal bridges. We still may have the condensation issues that are associated with it and thermal comfort issues if it's something like a balcony slab. And so that's sort of the downfall of that sort of approach to it. And ASHRAE has recognized that it's somewhat of an issue in terms of the ambiguity of the language surrounding thermal bridging and the 90.1 specification and how to deal with it. So I think it was around 2014 they first started to look at this issue and begin to study it and did some research work and then finally developed this last fall. They released an addendum to that specification. It has many updates and types of the language around surrounding thermal bridging. It turned out to be one of the most commented addendums they've ever had. They're still working their way through those comments, but it's my understanding that I think it's going to go out for one more cycle of review and comments, but they would like for it to get into the next version of that energy specification. And it begins to tighten up the language quite a bit surrounding thermal bridging. And then one of the things that it's doing, it's starting to get into a little bit of thermal modeling that's a bit different than what we're used to seeing. Now, we're used to just doing com check, res check, things like that to get to compliance. But there's going to be a little bit deeper level of either calculation or other parameters that we have to look at as we're beginning to come into compliance or with the new language in the energy code. So what I want to do now is to talk a bit about that building science and what that might look like going into the future. So that we're going to thermally model this type of detail. Then what we want to do first is define three terms so that we understand what we're talking about. First term we want to define is what's called a clear field transmittance. And a clear field transmittance is basically the overall U value that we have for the building envelope when there's no penetration. Second parameter we want to define is a linear transmittance. And a linear transmittance is going to be something like a balcony slab, kind of a long linear element, or maybe something like a masonry support angle. And that linear transmittance or linear thermal bridge is going to be measured with the Greek letter psi. And then a point transmittance, something like a canopy beam, will be measured with the Greek letter chi. And then if we want to capture their effect on the overall performance of the building envelope, then what we need to do is we need to add in their effect to the clear field transmittance to get the overall performance of the building envelope at that detail. Okay. If you really want to calculate those funny Greek letters, and to get those parameters, and what you have to do is you have to create two thermal models, one of the clear field condition with no thermal bridge in it, then one that has the thermal bridge in it, and that difference between those two models basically gives you that parameter. But I don't know that many of us that want to do that on a regular basis, particularly early in design when we're trying to make big decisions and things are changing quite a bit. ASHRAE realizes that as well. They're trying to sort of work that into the language as they go. But one of the things they've done to try to help us with that is they developed a research report that's basically a catalog of details. A lot of these things are pre-calculated. That research report was then later expanded by the same company who did it for them into the BC Hydro Building Envelope Thermal Bridging Guide. That thermal bridging guide is constantly being updated, and that catalog is just getting bigger and bigger. And so it's good reference, particularly early on as you're looking at those big decisions to kind of say, look, my detail looks something like this. I'm going to use that number for now as we go forward before we refine the design. But if we were to go through that thermal modeling process and see how that kind of works step by step. So this is the detail from that thermal bridging guide. So it's a steel building, fan deck with concrete slab, steel stud walls, bad insulation between the studs, and some continuous insulation on the outside of that wall. And then we have a beam penetration through the building envelope. So if we were first to ignore the beam penetration and just calculate the overall clear field transmittance, then the clear field transmittance for that wall ends up with a U value of about 0.054, which corresponds to R value of about 18 to 19, so a reasonable wall. But then if we include the effect of what they're calling a linear transmittance, and we'll get to that in just a second, and the point transmittance, the beam, include that effect into the overall performance of that detail, and they get the U total value, And what we find is that U value increases by about 3 times, which means our R value drops from about 18 to 19 down to about 7. Quite a large impact at that slice of the building envelope where that detail occurs. And then if we look at where most of that's coming from, it's that steel beam. Now, just to note, they also say there's a linear transmittance in here. It's very small. They say there's a linear transmittance at the slab, even though that slab doesn't come all the way through the building envelope. And the reason they say there's a linear transmittance is because that bad insulation between the studs, it comes down, doesn't pass by that slab. It stops just where that slab. So you can see in the thermal model, they get a slight amount of increased heat flow there, but not enough to make a huge difference. So it's basically all just coming from the steel beam. But that's how that process would work if you were to go through that step by step in very, very minute detail. Language in the specs, you're going to have options to make it much simpler and just either tabulate it, or if you really want to go to that level of detail, you can go ahead with that. Okay. But if we're going to talk about solutions to solving these problems, then the other thing we need to talk about is condensation and condensation control. And this is not something that ASHRAE gets into so much because they are an energy specification. We've talked to them about it. I say we realize that, but our scope is basically looking at the overall energy performance of the building, not that the rest of this stuff, but it's still an issue. And so what we want to do now is talk a bit about the science of both measuring that condensation risk and what we might do to mitigate that risk. Okay. So if we want to look at the science behind it, we're going to use that same detail we looked at before to study this. But what we want to do first is define what's called a temperature index. And a temperature index is basically just a ratio between our interior surface temperature of our building relative to the inside and outside air temperature. Now, this ratio can vary anywhere from 0 to 1. If it's at 0, that means you don't have a building envelope. That means your interior structure is as cold as the outside air. If it's at 1, that means you sort of have the perfect connection at the building envelope. You're not getting any more heat flow than you would through your insulation layer. That's never going to happen when we have structural penetration. You're always going to get some sort of increased heat flow. But the idea is to minimize that and get this temperature index up to as high of a level as we can, to have a little to no risk of condensation. So that's the way we can measure our detail. But now we need to compare that against something to understand what type of risk we're going to have of condensation. And to do that, to determine what's called a critical temperature index, basically that temperature index where we're going to have condensation, you got to go to ASHRAE psychrometric charts, or as I like to call them, psychometric charts, because they look so crazy. This chart is basically just a relationship between interior air temperature, relative humidity, and dew point temperature. If we want to use it, which I don't think most of us want to use it, but if you were to try to use it, you start on the x-axis with your interior air temperature, go up to what you think the relative humidity is, follow that across to the saturation point, and then back down, and that gives you the dew point temperature. And you can use that information to calculate a critical temperature index, or a temperature index at which condensation will form. But most of us, if you're like me, don't want to use that on a regular basis. So one way to simplify it down is just ask your mechanical engineer or do the exercise yourself one time. Say, look, I know roughly what my temperature ranges are going to be in my relative humidities. I'm going to create a simple table that tells me all of that information. And so I just have that tabulated somewhere. So that's one way to simplify it. Another way you could maybe simplify it, this is what our building codes don't address so much, but in Europe, they get a little more into this. In the UK, they say, well, we're going to get rid of all of this, not make you calculate that. We're just going to do it based on building type. Because we know roughly what our relative humidity should be, and because they're a fairly small climate zone, they can do this type of thing. But we're going to use this as sort of a proxy, because it's good rule of thumb numbers to kind of keep in our head where we need to be. So what they do in their specifications is they say for office buildings, keep your temperature index above 0.5 if you don't want to have a risk of condensation. For residential buildings, keep it above 0.75. And for residential buildings, the relative humidity level is usually higher. So that's why we want to keep that temperature index higher. Okay. Now, if we go back and look at the same detail we've been looking at and say, well, how is it impacted? Both if we don't do anything, and then if we try some solutions to try to fix it. So if we don't do anything, our conventional case, uninterrupted steel beam, it goes right through our building envelope. For this particular detail, that will have a temperature index of about 0.52. So it's marginal for an office building. You might have a risk of condensation, you might not. You're kind of at that boundary where you might have a problem, you might not. But what's interesting is, one of the solutions to try to fix this, and we're going to talk about it more, is to use the thermal pad, which is a okay solution if you do it the right way. But often what we've seen in drawings that have come across our desks with these types of solutions is that they're specified at very thin pad thicknesses. But what happens is if you use a very thin pad, you actually get negative performance here. Your temperature index drops. It's not until you get out to about 1 inch thick with stainless steel bolts that we basically get back to the same level of performance that we had previously with just that continuous steel beam. If you want a nice improvement, you need to be 1.5 to 3 inches thick. And we're going to talk about that a bit more, why that's the case, why you get this negative performance, and why you need to have a thick insulation layer. Shook solution, the one we'll pass around in a minute, it's kind of a manufacturer modular solution, tries to wrap all this, what we've learned, up into one solution. And we can get temperature indexes up to about 0.79, which is basically in the gymnasium range without having condensation issues. Okay. So we've talked about kind of where the building codes are headed, the thermal modeling side, and some of the condensation issues. What we want to do now is look at solutions that are available on the market, some of their strengths and weaknesses, and kind of where the sweet spots for them might lie. And so the first solution we want to look at is probably the oldest one in the book. And that's just to wrap the beam in insulation for a few feet, either inside, outside of the building, or both. Advantages of this type of solution: it's fairly cheap, easy to install, pretty straightforward, but not really any additional materials that we're haven't used before. But the challenge is first of all, it's not a true thermal break. We're still going to get a lot of energy transfer across that connection. When you use this type of solution, what you're really trying to do is you're trying to solve a condensation problem. And to give you an example of how that works, so this detail, you didn't put any insulation on it, its temperature index is going to be about 0.51. You wrap it for a few feet in insulation, you can move that temperature index from 0.51 to about 0.55. So it's a marginal improvement. But if you've got an existing building where you know you have a problem, you know you got condensation issues, and you've done your calculations, and you say, well, I'm just right at that boundary. The relative humidity level is a little bit too high. That's what's causing my condensation issues. If I move that temperature index just enough, I'm not going to have that problem anymore. Then wrapping that beam in insulation might be a great way to solve that problem. It's already in the field, you know you've got a problem. And so that's sort of the sweet spot for this type of solution. Sort of existing buildings where we know we have issues, and we know we're at that boundary, we just need to move just a little bit. Okay. The modern twist on that same idea is what's called a thermal paint. Now, thermal paint is basically, if you look at the manufacturers who make these things, it's basically an insulation material that's wrapped into a binding liquid and then spray applied to the beam, usually at fairly thick layers. In principle, it's the same as wrapping the beam in insulation. It just happens to be a different material, so they try to reduce that thickness. Has a lot of the same advantages of wrapping the beam that we talked about before, but also the same issues that go with it. In terms of, it's not a true thermal break, you still get quite a bit of energy loss across that connection. And its sweet spot, once again, is probably for existing buildings where we know we have problems, and we're trying to push it just enough that we no longer have those condensation issues. Now, something that is more of a true thermal break are the thermal pad solutions. And with a thermal pad solution, what happens is that where that beam penetration would come through the building envelope, steel fabricator will cut that beam in their shop. They're going to weld in place on either side to the beam. That beam is you're going to insert a thermal pad material between those in place and bolt it all together and kind of sandwich it together. Now, that thermal pad material can vary from manufacturer to manufacturer, but practically it's basically a piece of fiberglass is really what it comes down to. It's some sort of resin-based material, essentially a fiberglass. Now, the advantages of this solution is that because this is a piece of fiberglass or something like that, it just gets inserted between the end plates. We get a lot of flexibility with that head plate design in terms of bolt placement, things like that. Some of the drawbacks to it, we'll get to in a minute, but what I want to do first is talk about why we said before that we have negative performance if the pad is too thin. And we'll see that in just a second on the energy side of it. We showed you on the condensation side, but the reason you're getting that negative performance if you have a very thin pad is that we usually start out with a beam that looks something like this. So it's a wide flange beam. It's been optimized for a long time by the structural engineering community and the steel community to try to make that beam very efficient and very cost effective. But what happens is, once we cut that beam and we weld that end plate onto the end of it, we go from steel area of something like this to a steel area of something like that. So it's order of magnitude increase in steel area. And because of that very, very high thermal conductivity of structural steel that we talked about in the very beginning, don't get a thick enough insulation layer between those two end plates, you're going to get negative performance out of that connection. You would have been better off just leaving it alone if you're not going to use a very thick insulation layer. You really need to be 1.5 to 3 inches thick to get the type of performance that you probably are expecting out of the connection. On the energy side, once again, kind of the same chart we showed before, relative to basically doing nothing, you get negative performance up to about 3/4 of an inch to an inch thick, and they get a nice benefit in terms of energy performance and condensation performance. 1.5 to 3 inches thick is where you want to be. And then somebody's got to address the structural bolt issue where you have bolts that are crossing that thick of an insulation layer. But that's sort of the key with those types of solutions. The drawbacks to a pad solution, or the thing to keep in mind, is that it's probably more of a new design type of solution. No one wants to go out and cut the beam off their building after it's already in place, weld those in place on them, and bolt it back onto the building. It's more of a new design up front. We know we got an issue. We're going to try to take care of it. Okay. Now, the solution that Shook offers tries to wrap all of what we learned into one solution, and an engineered manufacturer modular solution. So what we do is we know we need to have that thick insulation layer. So we start out with a 3 1/8 inch thick insulation layer. And then the bolts that we pass through there, we make them stainless steel for the reasons that we talked about at the very beginning with that chart, that structural steel to stainless steel. You get a much improved thermal performance when you switch to stainless steel. Even though it's not great, it's still much improved. We'll insert these modules at the top and the bottom of the beam to carry the tension, compression, and shear that we have to transfer across that connection. But since we do have such a thick insulation layer, what we do to prevent these bolts from going into bending and carrying all that load and bending, if we were to strip away all of the insulation from around this module and just look at the structural pieces on the inside, because we're not relying on the insulation to carry any load, what you're going to see is something that looks like down here on the lower right. So you got the two stainless steel threaded rods that come through and act as the bolts. And then on each face of the module, there's a stainless steel plate. And then in between those plates, there's a stainless steel tube welded between them. And so that the load path is really, instead of bending those bolts across the connection, it's through that tube and then out the other side. And so that's how we try to basically deal with the thermal side, the condensation side, and the fact that we've got to carry structural loads across that connection. And then it's manufactured as a modular solution. Okay, so we'll pass this around so you can take a closer look at what that looks like. Okay. And then we can get energy improvements up to about as much as 50%, and then, like we said, there's really high temperature indexes that we talked about before. Okay. So some people look at this steel that we have going through the module here, and they say that still looks like quite a bit of steel. You know, how's that any different than what we just talked about with that wide flange beams, the end plate, etc. So if we go back and look at kind of that same situation we had before, we go continuous beam, cut it, put the thermal brakes between it. If we were then to take and cut, basically take a saw right down through the thermal brake modules that we would sandwich between those end plates, and what you're going to see crossing that insulation layer is this. So we only have the area of the bolt, or the threaded rod, and we have the area of the tube here. So we have reduced area in terms of the steel to just what we need to carry the loads across the connection. We're using an improved material, stainless steel rather than structural steel. And also because of how they're distributed across the connection, it helps with that temperature profile and temperature index as well. So that's how you're able to get that very high performance out of that connection. Okay. But just like with the thermal pads, this is not a likely solution for retrofits for the same reason. Don't want to cut that beam off that's already in the field. It's more of a new design type of solution. And because it is modular, those bolts come at a standard spacing for each module. The design of that head plate needs to be worked out during the design process. So that's kind of how that works. So where has it been used? We've been talking about steel connections in this presentation. And I don't know about the other manufacturers, but at Shook, and here in North America, we've done about, I think the latest project count is north of 320 projects that are either completed or under construction right now. About half of those are concrete, the other half steel-to-steel connections. And then quite a few of those projects are up in the New York City area. It's been our biggest market so far in terms of adoption and just uptake of these types of solutions. Okay. What I want to do is show you a few examples kind of scattered around both North America, but also the rest of the world, to give you a sense of what can be done with a thermal break. So this first building is up in Massachusetts, at the Life Science Laboratory up at UMass Amherst. We were asked to thermally break all these canopy beams on this side of the building, as well as the ones that were on the other side that you can't see there. I showed an image of it a few slides back. This is what it looks like when they came back and finally finished the thermal break. So between the modules, top and bottom, you just insert a rigid insulation, and that finishes the thermal break. And then they finish the rest of the building envelope, wrap that up, and you don't even know it's there. The loads are pretty high on this connection, so we needed multiple modules. That is one advantage of it being modular. As the loads increase, you just increase the number of modules in proportion to that. So that's before the beam's in place, and then afterward there on the right. Next project is that Minnesota Viking Stadium. We were asked to thermally break all the beam connections for this video board, this giant video board on the outside of the stadium. There's quite a few beam penetrations that come through. It's probably hard to see in the back a little bit. They're circled here in red, probably about 30 of them. They're just this beam stub with those same modules, one top, one bottom, to pick up those loads from the video board. More of a local project, the National Museum of African American History and Culture down on the mall. We did not have a huge part on this project. Ours was actually fairly small. We were asked to come in and thermally break some rooftop connections where the air handling units came through the roof. So what we did is we took that same module, turned it vertical, and used it more of a rooftop dunnage application. And quite a high compressive capacity. Another interesting project. I'm not sure yet if we're on all 7 continents, Australia being the one that I'm not sure if we ship material there to yet. We've got the hard one out of the way, and that's Antarctica. This is Brazil's research station down on King George Island. The one they had previously burned. They had a design competition for the new one, and the winning design was this, where they would, this superstructure, they would build as modules off-site and then bring in and basically bolt onto the foundation below. And we were asked to thermally break all the connections between this bracing structure underneath and the living module. This is what it looks like as they were constructing it off-site, kind of going through the first, kind of building everything, making sure it all fit together. I don't have updated photos. It's my understanding that it should be in place now in Antarctica, but unfortunately I don't have the updated photos for that. Okay. It gives you just a little bit of a sense of what can be done on the steel side with those thermal break connections. Okay, so just to summarize here, what do we talk about? So we went through kind of how thermal bridges happen, where they happen on our buildings, where the codes are headed, what that means in terms of thermal modeling, and how these funny new Greek letters impact our overall U value in terms of linear and point thermal bridges. We talked about condensation control and this idea of a temperature index to measure that and have a reference point. And then we wanted to look at some of the solutions that exist and their effectiveness. Now, what I hope we take away from this today is that, first of all, realization that these linear and point thermal bridges can have a significant impact on our U value at that slice of the building envelope where they occur. They can have increase the U value by multiple times, or drop that R value quite a lot. We want to avoid condensation. Good numbers to keep in our head in terms of rule of thumb numbers. Keep that temperature index above 0.5 for offices, 0.75 for residential. If you want to use a thermal pad solution, that's fine. Just make sure it's thick so you get what you think you're getting. 1.5 to 3 inches thick. And then somebody's got to design the structural bolts across that insulation layer. And then so you want a solution that kind of manufactured that sort of tries to wrap all that up into one, as well as we do a delegated design for that connection, then Shook offers a solution that way. Gentleman there on the left is the regional manager for down this way. Couldn't be here with me today, but his name is Aaron Chan. And then my contact information is there on the right as well. Are there any questions or maybe something you want to talk about that we didn't get to in the presentation? Yes.
Maybe earlier, I'm just curious, like, that deal with the issues with, like, which it's one of the next scenarios that you mentioned.
Right.
Like these, I guess, like this type of product is more.
So for a shelf angle.
Right.
We can take this solution we have here and turn it vertical and kind of make it work. And we've done that before. But one of the things we like to do, we're a manufacturer, that's how we make our money and stay in business. But we much rather be viewed as a partner in design. And so sometimes that means telling people that our solution's not the best for that application. We keep hoping that our R&D department will develop something specifically for that. But right now, probably the best solution that I know about on the market is made by a company called Faro, called their FAST system, where it's basically, I don't think they designed it as a thermal break. They designed it as a way to try to reduce the size of that shelf angle and not make it so heavy. But what it ends up being is basically a connection that has very little material crossing your continuous insulation layer, and your continuous insulation basically runs behind the shelf angle. And in terms of thermal bridging and things like that, it's probably about as good a solution as any on the market. And so you might, for shelf angle solutions, that's probably the best one to look at right now. Hopefully, sometime in the future, I can say, nope, Shook has a great solution for that. We can help you out with that. But for now, what we would do typically is take the same module you looked at here, or a lighter version of it, and turn it vertical and make those connections that way.
So stainless steel was obviously for other reasons.
Correct.
Avoiding rust. Has there been any research into developing a steel alloy specifically designed for a lower thermal?
That's a good question, and to my knowledge, no. And part of it is because stainless steel performs so well in terms of the thermal performance. If you get the right grade of stainless steel, its thermal performance can be as much as 70% improved over structural steel. And if you look at duplex stainless steels, which is sort of that modified alloy, somewhere between, it has a lot of the same properties as stainless steel, but it's still a little bit ferrous. It has a magnetal stick to it. Its thermal properties are not as good. And so if you use something like a marine grade stainless, like 316, you're basically getting into the best thermal performance you can get out of a metal. After that, you have to do things like switch over to some sort of fiberglass material. And then you get some additional benefits out of the stainless as well, the corrosion properties, things like that. In case for some reason moisture ever got inside the connection. We see that particularly on our concrete connections. We use it for the thermal properties, but in case moisture ever would get up inside of here, we don't want to have ever any sort of corrosion problem. So that's another important reason to use it there. Okay. Any other questions? Can I ask you a question? What do you think of this stuff? And it's okay if you want to say it's ridiculous and I don't ever come here again. That's fine by me. I'm just curious what people's thoughts are. Does it make sense? Does it not make sense? Too hard to put in a building? It's easy to put in a building, that type of thing.
I think reflexively it looks expensive.
Okay.
However, DC, when they do their review of your energy model, will force your energy model to have balcony slabs modeled as uninsulated walls.
Okay.
And could be a make or break proposition in terms of getting a compliant building. So it seems to me that this is something that would be really good to have.
As sort of a tool to meet some of that stuff.
In not just in an emergency where you discover that you're not compliant, but just to incorporate everybody.
Out of curiosity, what do you think is, when you say reflexively, you think it's expensive?
Well, it's stainless steel.
No, yeah, I understand. But, well, why don't I just tell you what approximately the costs are, and then you can tell me again if that still sounds expensive.
Yeah.
So for the steel modules, it varies a bit on what the price is. But in general, if you think of about $150 a module, that's a reasonable number to keep in your head. On the concrete side, we've really been able to push our costs down quite a bit on this one. I think the latest numbers we have are anywhere in the $35 to $50 a linear foot range for the concrete side, for like the balcony connections, things like that. And that's roughly where things would be at. So I don't know if that still sounds super expensive or if it's reasonable, but that's ballpark numbers for where costs would be.
No,
Well, we're in the same problem in DC. It's like,
it's something that I think in the recent past, when you take a performance path building into DC, you get through. And the energy modeler does what they do.
Correct.
And you get through. Well, now these kind of things at this level of detail are being looked at.
Okay.
And I think we should be better prepared.
Okay.
And include these kind of technologies in our building.
Have you tried before to with something like this? Then?
Oh, no.
Okay. We get some people that, well, the reason I ask is because we get some people that have, and sometimes maybe it was 3 or 4 years ago or whatever it was, and either the contractor didn't want to do it, so they put a really high price on it or something like that.
Yeah.
And we have taken the approach here recently that, particularly in places like DC, where it's kind of, we've gotten the feedback we're getting from architects and we want to use it, people are still a little bit skeptical. We're willing to come in and basically cut the price really low for that first building so that the contractor gets familiar with it, even if we're having to basically eating material as a loss, so that we get a project or two with the contractors, they get comfortable with it, and then if you do want to keep using it in the future, it's not going to be an issue.
So post-tensioning, how does this work?
On the concrete side?
Yeah.
So why don't I don't have it on this flash drive, I got it on my laptop. So we have a document that talks specifically about that. So on the post-tensioning side, so normally on a post-tension concrete slab with balcony, the post-tensioning strands run all the way out to get the balcony. The challenge with that, with our concrete material, is if we were to design to that really large compression force from the strand, it has so much structural material inside the thermal break that it becomes, from a thermal perspective, you're just undercutting the reason you're putting it in. So what we say for the post-tensioning ones, jobs, is to treat the balcony as an attachment to the main building. So what that means is that post-tensioning tendon that previously went all the way through the balcony now terminates at the edge of the main floor slab. If it's a dead end of the tendon, it's not a problem. If it's a live end of the tendon that for some reason needs to terminate at the balcony, then it becomes more of a challenge. We've had people where they were able just to sweep it to the side. If they didn't have to move it too far. That's been one easy way to fix that. There's been other cases where that wasn't possible. And so what has happened is basically we treat all of our connections as delegated designs. So our engineering team's looking at these as well. At that point where that tendon would need to come through, we're going to increase if we need to, if there's not enough capacity already, we'll upsize the thermal break size just to either side of that. And then in that space where that the tendon would need to come through, we're not going to put a thermal break. What's going to happen is there's going to be a leave-out spot, basically a pull box. That's when they pour the slab and balcony that they don't pour. It's just enough that they can drop a jack in, jack the tendon, cut the tendon, they'll put a strip of insulation right behind that tendon, and then they'll grab that small area, that small pull box area on the balcony side. We found from the contractors that they think that it's really simple to do it that way. They really have no issues, and our feedback from them with doing PT jobs that way. I've got a specific document that we put together that says this is the process, these are our experiences in the field with the contractors, but that's kind of what you do.
What's the layer on top?
This piece here,
Yeah.
that's a fireboard. So
That's
often
what you would actually step on, or you throw door threshold sit on?
So it depends on how the detail comes together. Often what happens, so this is a fireboard, this is a rail basically to hold that fireboard. Depends on where the threshold and everything lines up. It could come across, basically it could sit mostly on the concrete on the inside and a little bit on this side. It just depends on how that whole detail comes together and where we're at. Some of the balconies are stepping, this is coming in at the base of the step. And so sometimes you're just flashing over the top of it. It just depends on the detail.
That'll be exposed still.
Usually it's the continuous insulation that comes in line with it, or it's flashed over. So you get there. Any other questions? Okay. Well, unfortunately, I've run out of business cards, but what I'm going to do is I'm going to leave a PDF copy of the presentation behind that has my contact information in it. If at some point you do have questions or you want to talk about something further, please feel free to reach out to us. We'll do what we can to help. Thank you very much.